Good afternoon, everyone, and good morning for some. Welcome to the Intelligent Substation webinar. Just a little bit about myself before we start. My name is Ahmed Musa. I've been in the utility business for over 21 years. I've worked in various aspects of the utility with a lot of focus on the substation, as we are going to see. Worked in Pepco, First Energy, Con Ed, and PSENG. I've also started two consulting companies, 100% Energy Club and Electric Bridge Consulting, focusing on the future of energy and just traditional electric utility. I also been fortunate to be on the IEEE, the Emerging Technology Advisor, which would be kind of interesting for today's discussion, as a lot of the stuff that we do are kind of the emerging technology perspective, and I'm going to explain what that is. And as you can see, without going into much details, I do sit on several boards, and a lot of them have a focus on substations as well as cybersecurity. So again, just a very high level. If you have any question or comment, we're going to be together. If this is the first time taking a webinar with me, a little bit under 2 hours now. We'll take a break in the middle, and we'll have plenty of time at the end for Q&A. You could always revisit any of the maybe topics that you'd like. And if there's a specific topic that I'm not covering that you think it's beneficial for you, please let me know and I'll address it right away. So let's get right into it. And again, there's just a snapshot in case if you have any questions or about my background. This is like just a quick snapshot about that one. So why are we here? We're here because substations, in my opinion, are the most important landers. And I hopefully you'll be able to agree with me towards the end of this webinar. We're here because we have the future. We're talking about the 2030, the 2040, the 2050, the grid. As the utility of the future manager, New Jersey has a 2035 100% clean energy. That's a very, very aggressive goal because number one, it's very soon. And, I live in New York. New York has a renewable energy goal. And there's a difference between 100% clean and 100% renewable from that perspective. 100%, both systems in the future would rely on solar, energy storage, geothermal, hydro energy, if you have any hydro plant. Nuclear will only be included in the 100% clean energy. That's usually a mistake a lot of people may make. They may say, oh yeah, we have 100% renewable energy systems and we have a nuclear net zero. Nuclear is clean, but it's not a renewable. So that's why it's usually mentioned in the clean energy only. The more solar we add, the more storage we add, the more wind we add, there'll be an impact on the substation, which we'll address kind of maybe at a discussion at the end. And that's why I mentioned, not only do utilities have a lot of substations and they're building more for a lot of reasons that we're going to discuss, also a lot of developers are building a lot of DER, distributed energy related substations as well. So that's kind of why are we here for the future. As far as the substation, we're going to first start by discussing why are we here. So what is happening to the substation that resulted in the need to discuss intelligent substation? What are the key equipment? What are the functions that they do? That's kind of on a very high level. Why are we here to discuss as a foundation? Then once we discuss the key equipment that are typically located in various substations, then we'll talk about the intelligence really, because when you say an intelligent substation, substation, as some of you may know, there's a lot of stuff in the substation. The equipment vary by type, by size, and so forth. So the intelligence is not like you can just say intelligent substation. Is it intelligent transformer? Is it the breaker? Is it both? Is it the battery room? So we'll address this stuff. Then I'm going to talk a little bit about, something we're going to call the futures 3D. What is changing overall to the grid? We'll touch on the role of data, because one thing that I could tell you before we start, a lot of utilities, they went the route of developing, intelligent substations without doing any of the homework. They did not predict the amount of data, a lot of new data that they're going to get. When I say new data, I don't mean like data that wasn't there before. You didn't have a meter. I'm talking about the type of data. You're putting infrared cameras. So now how do you get back like video feed and stuff like that? We'll talk about the very basics, the power triangle, really the real versus reactive power. And then we'll differentiate substation data from distributed energy resources data. A lot of focus on SCADA. SCADA stands for supervisory, control, and data acquisition. The term, it's a very fancy term, but uh, really the first C, I mean the only C, the only D, that's what it's one is control, one is data. I've been very lucky to have worked at the Energy Control Center at Con Ed in New York City. That was the coolest job I ever had, and I had control. But for the rest of my career, the other 20 years, I mainly had a view only because I was not in the control room, and only the control room have access to data. So then you can see it's kind of a busy agenda, but we don't have a lot of slides, so we have a lot of time for discussion. So once we discuss about the future changes to substation, so in your mind, you should see, okay, we have all these changes and even more expected. What will be the impact? We'll talk about the transmission. How is the transmission changing? We'll talk about NERC PRC05, which is one of the tools that some utilities are utilizing to develop an intelligent substation. Because once you agree that this is the best thing to do in the future, the next step is, okay, so what do we do? We'll talk about infrared cameras. I'll show you some pictures. I'm personally a big fan of infrared cameras. Some are not, so we'll discuss why and why not. IT, information technology, it's a very, very important group. Without IT support and blessing, there's not much you could do, especially in the whole intelligent substation perspective. On a very high level, I mentioned solar before. So we're adding a lot of solar, a lot of energy storage. So we are introducing a new device that we have not really communicated to in the past, or at least have experience with, which is the inverters. Inverters, traditionally, all they did was they convert DC to AC. If you want to install solar at your house and you have a decent sized solar and you want to sell the excess to the grid, your solar system is DC, the utility system is AC. So you have to have this conversion from DC to AC. However, all the inverters now are pretty much smart. They have a lot of intelligence. So what could you do with that? One thing I could tell you, and you're more than welcome to take a lot of the other webinars we have, like solar, like storage, like EVs. Voltage control is becoming very challenging. That's for sure. The more assets we install, the more equipment we install, pretty much the more difficult the grid becomes, voltage control becomes very challenging. If you're not an electrical engineer, and if you're mechanical, voltage is pressure. Imagine like watching your TV, then the light is very, very bright, then the light is very, very dim, and the transition from brightness to dim, if you will, that's kind of what happens when the voltage is not really stable. We'll touch on transformers. Transformers are the most important equipment or component of the substation. And then what's after the 100%? And then finally, I'll introduce the robotics. So as you can see, we have a pretty busy agenda, but we definitely have the time for, we're not going to rush. And again, if there's any topic that you wanted to see, feel free. Just another reference to another webinar, we have a webinar called Substation Fire and Grid Damage. It's kind of like everything's bad news, fires, damages, failures. So I go into great length about what's happening to the grid during like major events like volcano, during like earthquake, stuff like that. So it's kind of a good transition to take. You could take it with this course, before or after, it doesn't really matter. So let me just stop here for a few seconds. Let me put out the chat, and then if you have anything again that you would like to see that I'm not really discussing, feel free to put it in the chat. Okay, so I'll do a lot of pauses. I'll ask you guys some question. If you can, it's good to be engaged. That'll be like very, very helpful as well. Okay, so 2030 is basically 4.5 years from now. A lot of utilities, a lot of cities, a lot of states, a lot of countries, they chose the 2030 to be the midpoint. To be the midpoint, basically that's the year we get the 50%. Some places 80%, some utilities even 100% net zero. But what's really interesting is when they determined this goal, they thought it's pretty far. But like I said, it's 4.5 years from now. If you watch soccer, that's one World Cup away. If you watch football, that's pretty much going to be like 3 Super Bowl. So it's going to happen very soon. Now, there are events that happen globally that impact the way we think. Just if you thought about what happened uh, to Spain when the complete shutdown, That was very interesting. And I know that they released kind of the latest update from today. So there's a lot of webinars already that are being discussed. And I have one, I think, I believe tomorrow that will discuss the cause of it. Initially it was kind of the East versus West. Some people told you that's because they have a lot of renewables and the system has low inertia. The other mentioned no, that we didn't have enough energy storage. And I'm reading now there's a failure at a substation that started this, so we'll find out. But the idea here, the point of this, I'm trying to connect you that anytime you hit 100% or 80% of something, don't just think from a climate change perspective. Think about the impact on the substation. Do you have enough? Do you need to change? Do you need to digitalize? That's the point, at least for the next an hour and a half, that I'm trying to express. Now, the 100% clean renewable energy, this is one goal. But the other goal that is getting even more power behind it are the three bullets in the middle. There is a forecast for solar, community solar, large scale solar, residential solar. There's also a forecast for wind, whether it's onshore or offshore wind. And offshore wind brings, I think, one of the most, this sector brings the most intelligence that are required. Why? Because number one, the stations are unmanned and they're in the middle of the ocean, so you can't just like drive there. And if the weather is very nasty, you can even get a helicopter to take you there. So that requires the most intelligence. Nowadays, under the latest administration, things are not looking very great for the wind industry, but nevertheless, we just wanted to highlight this point here. Energy storage is the one that's getting the most between solar and wind and solar and storage. I just read 2 weeks ago that I believe in Emirates, they installed the first ever 24/7 solar site. It's a gigantic site with, I think, almost 19 gigawatt hour of storage. So it's a massive solar, massive battery. It is so big that you could pretty much run around the clock. You charge through the solar, but there's enough solar to charge. So again, we're seeing stuff. So why are we discussing this again? Because if you're gonna put like 19 gigawatt hour of storage, that means you've built a massive substation or multiple substations to accommodate that much power, if you will. Now, as far as generation, so I mean, I've been teaching this course for a while. So initially, there was always a discussion that the fossil fuel generation is kind of getting extinct. But now with the latest, with AI, data centers, load growth, and the government kind of appetite for fossil fuel, it seems that natural gas and even coal may be here for a while. So let's start right away. So we're starting from the basics. Again, what I like about the substations is that you can never say I have seen every design. Even when you say like this is known as a straight bus design, you see the horizontal bus. You got two transformers, two lines feeding the bus, and from the bus, you got like four circuits connected below. And basically, there's a normally open point, which is that green breaker that you see in front of you here. So on a very high level, under normal condition again, these represent two different substations connected together. So under normal condition, which is like 99% of the time, two stations completely independent. But if you lose like one of the transformers, the other side will kick in after like a momentary interruption or a long interruption. And then, so that's known as an N-1 design. So you lost a component, which is the N is normal. So it's normal minus one. So basically it's not normal anymore design. So I want you to imagine this very simple design. That's the starting point globally. Again, this is not just in the US. And then you could see here, the circuits in the bottom, they are radial. Radial is also the least reliable design. To this. So let me give you a full minute. So again, we're going from this to this. So let me give you a full minute to just read all the blocks, all the text I'm writing, and notice all the connections now between feeders, and I'm going to explain all the addition for that one. All right, so again, we started with having just basically two transformers, four circuits. Now we have the same thing, but number one, we're showing another substation. Now it's very common for the supply feeder to supply multiple stations. We don't have unlimited amount of circuits. So that means when you lose that circuit, you lose multiple substation transformers. That's number one. Number two here, you're seeing connections, if you could see my mouse on the bottom left, between circuits. So now we have ties, which is like a normally open switch that connects different circuits from different feeders. It gets even more interesting. We're seeing connection on the middle right of connecting buses together. And this is usually is unheard of because of the phase angle, the short circuit. So, but some locations, that's what they do. We're seeing that big solid arrow with solid line with dual arrows. We're seeing a connection between circuits from different substations completely. And as far as the addition, we have solar. Again, I'm only showing like maybe solar in one circuit, but they all could be the same circuit. I'm seeing solar, fuel cells, distributed generation, batteries, vehicle to grid, which is EVs sending power back to the grid. We're seeing demand response, which is DR, DSM, which is demand side management. We're seeing capacitive banks, mobile capacitive banks. We're seeing a clean emergency generator, let's say using biodiesel, and we're seeing emergency generator just like using regular diesel. So we're seeing a lot. And again, notice the connection we have. So the circuit on top right, it basically is out of service, but we're still able to send the power through all this generation from one feeder to the other. So again, what's really interesting is all the stuff I mentioned, they all could be on one circuit. And we're only in the year 2025, and this system technically exists like that. So I'll give you just a few seconds to take a look, see if you have any questions or comments. Okay. So again, so from one perspective, just the reason I'm showing you the slide, because for some people, in their vision, intelligent substation means a station that could accommodate renewables. It could accommodate like CHP fuel cells. I mean, I'm not saying they're right. I'm not saying they're wrong, but having DRs interconnected doesn't make you smart or not. It just makes you basically flexible to accommodate DRs. So now, before getting to the intelligence, one thing for sure, not all the substations are important. So let me pick on somebody. So we have John and Roger, for example. Both of them are brand new operators. This is their first day at the desk, and both of them came from different utility or even different fields together. So if they're sitting there on the desk and they're unlocked the first day, the emergency phone rings, and they could, for example, say substation X is on fire. They have no idea. Is that a problem? Of course, it's a problem because the station is on fire, but how important the station is, what will be the impact to the grid, and so forth. This is the stuff that you learn by experience. But one thing that is done more often, which makes life easier, is when we refer to the type. So, for example, if we said switch yard X, Y, and Z is on fire, or transmission station X, Y, and Z, or sub-transmission X, Y, and Z, that makes it much easier to understand. And that's kind of the point that I wanted to raise here. Uh, just the fact that you know the type tells you a lot. And again, if you take the other webinar with us, we get into a lot of details about, from a fire perspective, damage perspective, what's worse, damage at the transmission station versus switching station. So again, here, I'm gonna make it very clear. I strongly believe substation is the most important piece of land. Without a substation, life as we know it doesn't exist. Even if you have solar, if you have renewables. So the first station, the term switch yard, that's the term that was basically chosen. So anytime you hear the word switch yard, you gotta basically pay very close attention because that's a substation at the power plant. So if they have a disturbance at a switch yard, that's a big deal. So again, if John gets a phone call that there's a fire at a switch yards X, Y, and Z, he need to pay attention because depending on how many power plants and how large it is, that will become an impact. Because for example, if the station is down, even if the power plant is 100% operational, it's going to go down because you don't have the ability to take the generation elsewhere. So I hope this point is clear because this is very important, which is the switcher. So again, the picture you see on your right, that's a picture. You can see the stacks for the power plant in the back. It could be like a gas turbine, and you could see the step up transformer. So generation, typically, they generate voltage between 11 to 22 kV. That's medium voltage. And of course, I live in Queens. Right now, we are building lines from upstate New York and Canada to New York City. So you're not going to have a straight shot, just one line from there to there. Also, the power plants, the generation business, they generate power at what's known as medium voltage, 11 to 22 kV. Imagine having like a 500-mile circuit that is 11 kV. I mean, the distribution, I mean, that's like a distribution voltage. The voltage is going to collapse very soon. So that's why we create the transmission system. So the transmission system really starts right at the picture you see in front of you at the secondary side of the transformer. So it goes in as 11 kV, then it exits, let's say 345. The most common voltage in the country is 345. The highest voltage in the US is 765 kV, but globally we have like 1.2 million volt that exists. The higher the voltage, the more the capacity. So you could argue, why not build, the 1.2 million volt in the US? Yes, it's high in capacity. That means if you lose a circuit, you lose a lot. Number two, it's a massive design. Most likely, you will never get the approval to build such a gigantic tower. It's kind of, you see it in like China and other places. They have a lot of land that, basically a lot of rural land. So it's kind of easier for them to do something like that. So again, just imagine you have a transmission station and then you have a switching station. So let me ask you guys kind of a quiz. What's the one difference between switching station and transmission station? So take your time and just put in the chat, please. The question is, what's the difference between switching and transmission station? There's one main difference. Any guesses? Okay, 10 more seconds. Okay, so the example I gave of connecting Canada to New York City, imagine it's going to be a 345 kV, or so 345,000 volt line. You're not going to run a straight shot all this mileage in one shot. If there's failure, if there's inspection, if there's maintenance, you're going to lose the entire route. So what you do is that, after X amount of distance, they would put like, a transmission station, it's going to have breaker, metering equipment, and so forth. That's what it's going to have. However, usually when you say transmission, that means the voltage going in the station and the voltage exiting the station is the same. So it's 345 coming in, 345 going out. When you hear the word switching, that means there's a large power transformer involved. So you're stepping down basically from, I'm sorry, it may go 345 and exit 345, but also a couple of lines in parallel will come in 345, and then you have 138 kV. So it's in and out. So it's possible that the voltage stays the same, but also you introduce a new transmission or sub-transmission voltage. So let me stop here for a minute. Make sure you understand the difference between the two. If there's any questions. It's a relatively quiet group today. Okay. Now you should, again, we're not here to talk about damage, but you should make the conclusion right away that as far as risk are concerned, switching station, pose more of a risk because you have all this oil-filled transformer compared to transmission station when there's no large power transformer used. Uh, yeah, so Thomas, thank you for that. It's the opposite. You know, it's basically a trend because think of it, switch. I mean, look at the term switching. What are you switching? You're switching from voltage A to voltage B. So that's kind of, I know it's confusing. Everybody gets this wrong. So when you hear the word switching from now on, that means there's a large power transformer. But thank you for sending the comments. So what is substation? I mean, there's a lot of definition. You have here one, a set of equipment reducing high voltage to like a suitable voltage. I personally created the definition at the bottom. You receive the energy from generation, you transmit this energy, then you distribute this energy. The beauty of the power system is everything is in the name. Distribution, you distribute, transmission, you transmit, generation, you generate. Also, now once you get closer to the distribution side, there are a lot of different names. Some people just call it distribution substation, some call it area substation, some just substation, some you put the voltage, for example, 13 kV station. And then at the same time, there are different types. So let's speak on somebody else. Let's say Paul, he's an engineer and he get a load letter that they're going to build a new mall. But Paul knows it's going to be a while before the mall basically reaches full potential. So what he does is he put a unit transformer. Unit transformer, as the name implies, it's one line in, one line out, or maybe two lines out, but it's one bank usually. It's called unit. And usually, if you don't have a lot of load demand, it's a safe bet to start with, and it's like cost effective. And then later on, when Paul was doing the work, he gets another forecast. I know the customer, the load grow. So now they basically end up maybe having like what's known as a multi-bank. So they basically parallel the existing bank with another one. So from a perspective of damage, unit substation probably has the least impact compared to others. Some utilities that, and I'll give them credit, they have the mobile substation. So either during emergencies or during construction, they're able to basically roll in or like drive a mobile substation. Again, it has its certain voltage, of course, and so forth. So let me stop here for a few seconds. See if you have any question about the station type. I thought somebody was starting something, so let me just wait a second. Okay, now that we kind of know what the different substations are, at least the name, the next thing really is to focus on, what do they do? So number one is a transformation. Again, I gave you the example of going from Canada to New York City. Yeah, if you didn't have the step up transformer to go from, let's say, 11 kV to 345, you're not gonna have such a long line. And then at the other end, you go, let's say, from 345 back to like 11 kV. So you have transformers at the substation to allow for the voltage transformation. That's the most important use case. Then it's regulation. So again, going back to the voltage is pressure, going back to the light being very bright and dim. Imagine watching like, your TV show or your favorite game, and the light keep changing as well as the TV becoming very bright, then very dark, then very bright, then very dark. So that's kind of what it is. So we have tools at the substation to regulate the voltage to ensure the pressure is adequate. And then we kind of spoke about SCADA very quickly, but it's data is very, very important. Without data, we're flying blind. That was one of the lessons learned in Superstorm Sandy. We did not really have that much data to rely on. So again, as far as data, you have the feeders. You have, for example, the voltage, the current, the real power, reactive power, and so forth. You have the power factor as well. If you have an underground transmission cable in a utility that uses oil, so you can have oil basically in the pipes. You need to check the temperature, check the pressure, circulate the oil. You have the traditional like transformer voltage, current, load tap changer, and so forth. And then you have other equipment type like circuit breaker. Really, is it open or is it closed? Are there any alarms coming from having like inadequate, for example, SF6, or what's going on? And then you also have a status, really, like I said. So sometimes you have an actual data coming in, which is like analog numbers or digital number, and sometimes it's just a status, yes or no. So, it depends. I mean, we don't like magically get the data. You have to put equipment known as instrument transformers to measure the voltage and current. And then as far as the temperature monitoring, this is very important. You cannot have an intelligent substation if you don't basically monitor the heat of the system. That's very, very important. Um, okay, I see a question that came in. I'll answer it, Roger, 1 second. So again, the temperature monitoring provides a lot. So inside the transformer, when it's really running hot, you check how close are you to the IEEE limits, and if you're very close, you have to take immediate action to save those equipment. Yeah, so now I guess the question, I mean, if referring to when I was saying the difference between switching, I mean, just if you don't mind, Roger, because I know you sent this like a few minutes ago. Difference you mean between transmission and switching, or difference in what? So if you can maybe explain what difference are you referring to, I'll be able to answer your question right away. Now, another thing which is important here is the renewables. So whether we like it or not, renewables are part of the grid. They're here to stay, and they're being built everywhere. So uh, in addition to the real reactive power and all the stuff, we also have the solar radiance and stuff like that. So again, Roger, if you don't mind, you could just like update your question so I know what to answer. If you're referring to the difference between switching and transmission, or from what perspective. Thank you. All right, so let's just spend a couple of seconds to look at the slide. Okay, so the list continues as far as key functions, switching and protection. So we do a lot of maintenance work. We do scheduled work. The example I gave of Paul getting like a new business, which is the mall, and going back to do the work and to identify how they're going to connect at this customer and by when, but you need to do some switching moves. You need to make it safe and reliable for the crews to work. So again, all kind of switching, whether it's done for normal condition or emergency condition, is done via substation equipment. System protection is very important. You can see the picture on the right of basically a cap can that blows up. So we need to make sure two things, that life goes on after an interruption. That's very, very important. And then um, if the next step is you need to make it safe. So you detect the fault very quickly, isolate the fault, then you provide the most efficient kind of plan to fix that fault. So again, it's let me go back. Transformation, regulation, metering, switching, isolation, and protection. So no questions about this. Let me just see here. Yeah, again, Roger, if you could maybe enhance your question, unless I've already answered, you could just let me know in the chat. Thank you. So before making something intelligent, we need to find out what's in it. I mean, is it worth being intelligent? Is it worth the spending or not? So here, the king, if you will, or the queen, is the substation transformer. It's the most expensive and the most dangerous asset there's. Any reason why is the most dangerous asset to have in a substation? So I kind of mentioned this before, that the substation transformer is like the one that gets the most attention. So why is that? Why is the substation transformer get the most attention, and why is it basically always at risk of events? Okay, thanks, Roger. All right, so again, I just made a statement saying that the transformer, oil field transformer, is the most critical component of this intelligent substation. And I was asking the question, why do you guys think, maybe you don't even agree. So do you agree, yes or no, and why? So stop here for a few seconds. And part of the answer is already mentioned in the first bullet. Okay, Paul, thank you. Yes, it's a very important entity. It provides power 24/7. Without transformers, we're basically in the dark. But there's another point for the intelligence piece. Why else? Thank you. That's a great point. Okay, excellent, Roger. So basically, if and you kind of hit, we have to monitor the temperature. If the transformer gets extremely hot, whether for something loose, something damaged, or just because of overload, it's gonna be a problem. And you are right, 100%. And basically, the answer really is it's an oil-filled equipment. That means it produces the most risk, and it has thousands of gallons of oil. If you remember, when you're trying to maybe do some French fries and you almost burnt down the whole house. That happened to me once. And look how little oil you had in the pan. Now imagine having thousands of gallons. What's gonna happen? So that's kind of the main reason for it. The high heat. Yes, thank you guys. Great job. There's another transformer type known as instrument transformer. So we mentioned SCADA before, but think of it really. Do you just I mean, imagine you have a massive transmission line. Do you just throw a plug and run a meter? The answer is no. You basically put something called instrument transformer. There's two of them, the CT and PT. CT is current transformer, PT is potential transformer. So they basically step down the very, very high current magnitude and the very, very high voltage magnitude to a much lower level that we could use. For example, it could be 2000 amps and you only get like half an amp. It could be again 500 kV line, like very high transmission, and then it becomes 60 volt. And I don't know if you're able to see my mouse, but if you could look at the picture on the right, you could see this transmission SF6 breaker. You see this kind of cylinder in the bottom. There's like six of them. That's what a CT looks like. So the current goes at a very high level, and it basically provides you a very low level. So this CTs and PTs, they provide great value because they provide the input for the relays, and they provide the input for the SCADA as well. I think after the transformer, the one entity that gets the most attention is the breaker. So when we say breakers, similar to the substation type, we basically refer to the type. Is it oil circuit breaker? Is it SF6 circuit breaker? Is it, what type of circuit breaker it is? And of course, the oil in general in the utility, oil is It's kind of has been a problem from an environmental from a while, because oil leak, there's oil fires and so forth. So oil, we're trying our best to stay away from oil. Uh, so again, the breakers, they are great candidates from a substation intelligence because, number one, the breaker provides a very important function because if there's a failure and the breaker doesn't operate, we're going to have a major issue. You could have a fire, you could have you could lose the whole substation. So that's kind of very, very important. We use a lot of switches. Pretty much every important device you could think about is like a breaker or transformer is going to have, one switch on either side to be able to take that component out of service. So, we need to have always the means to operate in a normal condition and emergency conditions. Buses basically is like an extension cord, or when you have like a power strip at your house, you have one plug coming in from the wall, power strip, you could plug in a lot of stuff. Similar kind of concept. So from the transformer, you could have a piece of bus, then you have multiple circuits. So the bus is sometimes it's aluminum, sometimes it's copper, and so forth. Relays, you can see the picture here. I'm showing an SCL relay, the microprocessor one. Relays are the brain. If you don't have relays working properly, once you have failures, you can have very, very bad results. You could have extended outages, you could have failures, fires. So part of the intelligence substation is to make sure that the relays are doing what they're supposed to do. Uh, Kind of similar, if SCADA is not working properly, then you don't really have any intelligence. And that's a big issue. And a lot of utilities now are doing something called data governance. They're trying to find out, who's responsible for what. When there's an issue, how do they find the issue? How do they flag it? How do they fix it? Uh, when I was like in Manhattan, for example, and some parts in the other boroughs, that time we use a lot of underground cables, and they utilize oil. Oil is being used as an insulation and for cooling. So if you have a lot of oil, you need to move the oil around. So you have pumping plants to move the oil around to lower. I mean, the whole point is you're trying to get rid of heat. And then one which we're going to focus a lot on today is the battery room. The battery room plays a very important role. When there's a fault, we use the DC power of the battery to open the breaker. So if the battery is dead and a fault happened, we will not be able to open the breaker to isolate the issue. I had this once in my career. The battery was dead. The alarm didn't work for whatever reason, and the whole station basically burnt because there was a failure. The failure was not detected. So let me give you a few seconds here to go through over this. If you have any questions or comments? Yeah, nothing. So the list continues, of course. You could see here. Uh, the control room is a very interesting. If you've ever been to a control room, there's not much, but there's a lot. Thousands of wires. You have the meters. You got the communication. You got the SCADA. So it's not like a high voltage room. There are no oil-filled equipment and stuff like that. Yet it plays a very, very important role. So, and then station light and power. So one lesson learned from Superstorm Sandy, for those of you who were there a long time ago, the station light and power, it does exactly what it said, light and power. It's a very small transformer that provides like, local usage. Like basically, if the station goes down, the station light and power could be utilized to charge the batteries for the battery room, lights, computers, stuff like that. So it's very important. One of the lessons learned from Superstorm Sandy was that if you have like an oil-filled system, you need to already have either a backup diesel generator on site or have the connection ready. Just imagine like if God forbid you ever been part of a fire in New York City, the fire department goes outside, open the hydrant, direct the hydrant to the building, and then depending on where the fire is, they pick up the water from other places. So that's kind of similar to that. Uh, I mentioned voltage control as an issue. So when the voltage is too high, if equipped, we energize a device called shunt reactor. You could see the picture on the left. That's what it looks like. It's an oil-filled shunt reactor. The opposite to that is something called capacitor bank. I may have a picture later. That's a device to supply reactive power. So shunt reactor lowers the voltage, cap bank raises the voltage. So it's expected that if the offshore wind industry picks up again, not only are we going to be building a lot of substations, we're going to be adding a lot of shunt reactors because when the voltage rises at early morning hours when you don't have that much load, but you have a lot of wind generation, that's going to become a problem. Lightning arrestor, again, as the name implies, it arrests lightning. It attracts lightning from the sky and then basically bring it to Earth, if you will. So that's another important point. The ground switch is done before the station is built, and that's kind of part of the grid. Just an FYI, the picture on the top right, that's for a switch in the open position. Picture on the left, the shunt reactor. The picture on the bottom, that's basically what's known as a series reactor. It's basically an impedance. So you learn back in school, you add like a resistor and a reactor to induce impedance. So let me see if you have any questions here. See much. Okay, so let's imagine now Thomas and Paul, they wanna implement this. They wanna start having an intelligent system. Where do they start? So what some utilities have done, they utilize NERC PRC05-2. It's like a very fancy name. Basically, it's for protection system maintenance. So if you read, this is a copy and paste from them. So NERC again is the National Electric Reliability Committee. So they, or council, I forgot, committee or council. So they come up with all the rules to ensure reliability for the grid. So, you cannot have a reliable grid if the relays are not operated good. You cannot have a reliable grid if the battery rooms are not charged to act when there's a failure. So here, to document and implement programs for the maintenance of all protection system affecting the reliability of the bulk electric system so that this protection system are kept in working order. It's very simple, very clear to understand. So again, that's kind of the concept here, if you will, to do something like that. So as an example, here there's a battery type. So for a certain battery type, the plan was you have to visit that battery once a month to do basically verification and inspection that this battery is expected to operate as expected. Now here's the interesting part. Let's say today is May 21st. You go there, Paul goes there. 5 minutes later, something happened that the system failed, but you don't have the appropriate alarms or anything else. So then a fault happens, then the whole station shuts down. And at the same time, right now it's hard because we're trying to reduce O&M, we're trying to reduce spending, and if we have hundreds of substations, so if we have to go to every substation, like let's say once a month to look at some kind of data points, it's not the best use case for the resources. So what they proposed is, why don't we install like intelligent, pretty much intelligent battery systems, and I've seen a couple of them. So basically, they provide the verification and inspection all the time. So instead of you going to look at the car, imagine like I'll give you the best example. Back in the days, I used to have a Honda Civic, a very old one, and I mean I'm talking about long time ago. So I mean I only paid attention if the check engine light is on, and sometimes I don't even believe the check engine. So a lot of time I would put basically check the oil. The car has nothing, not a drop of oil. And if you know something about old Japanese cars, they could pretty much run even if I put water. Versus nowadays, the cars, they just don't stop talking. They tell you everything. So that's kind of the concept. Do I want to keep checking, the if I have oil, or do I want to get a sensor only when it's like maybe 30%, 20%? So that's kind of what they did. So again, this is very important. So the utilities, some of them, they saw that there's an opportunity and they took it. And the opportunity basically is to implement this automated system that would save them the time and effort. So, I mean, I was going to actually ask you guys the question, but I have the answer here. Now, I'm going to give you a couple of reasons, and I'm going to see if you have any opinion for something I missed. The number one reason is always O&M savings. Like I said, the best example I want to give, you put a system, it's up and running, and you no longer have to visit like 100 plus sites every month. I don't quite agree with this because number one, you're going to go there, you have to go multiple times, different vendors have different designs. A lot of vendors tell you have to pay for my software every year. Some of them require calibration, so it ends up costing even more. I'm a big fan of the second one. You're putting these tools to damage prevention. The example I gave when Thomas went to the inspection, left 5 minutes later, something happened and the cell collapsed, and now the battery is depleting and is dead. That system would have shown that. Data into investment. Now that we have a lot of data, the data, if you have like a data science group, and I'm doing a lot of stuff with artificial intelligence, AI, but if you have like a data science group, you could take all this input, all this output from the equipment and have some kind of intelligence. And lastly, there's a big push for all of us to extend the life of the equipment. Right now the supply chain, a transformer that the wait used to be like a year and a half is now 4 years. So we're doing everything in our powers not to lose any equipment, especially those with a very long lead time. So I'm going to stop here for a full minute. Did I miss anything? Any other reasons you believe you need to have an intelligent substation? Any more second? Okay. So I think that's kind of good news that I basically covered kind of all the points that I wanted to address. So as far as the monitoring candidate, so again, just a very quick recap. We established a lot actually. We established that what a substation is, the definition, the different equipment, the candidates. The equipment, and now we're about. This is gonna be interesting because if you guys are, let me see if there's a question that come up. Yeah, Roger, to your point, that's another challenge, really, like load balancing, especially right now when you have a lot of, like if you look at California, every day they have a lot of sunlight, a lot of solar panels. So every day in the morning, the power plants are supplying less, less, less because the solar is supplying more, and then vice versa at night. So that becomes a challenge. So that's a good point. And one of the biggest, in the control room, the big challenge for the energy dispatcher is doing exactly that. There are also stuff in the power plants called governor to kind of fill in the blank because it's too quick for an operator really to do all the stuff. We're not like, we don't move in like the speed of light. So here I'm gonna have a lot of slides. Maybe we'll address, those sets of slides. Then we'll take the first and only break. So we kind of, from a monitoring candidate, like a lot of time, it's not what you expect. So for a lot of people, especially in IT, their first candidate will be the communication system, the IT system. Because in their mind, if the IT system goes down, then we're clueless. We have no communication. We have no control. We have no defense. So it's up to you to think if this is like should be like the number one reason or not. I mentioned that we were in the business of getting rid of oil-filled equipment for an environmental reason. So we decided to go on the SF6 route. But what's really interesting is now that a lot of the stuff is SF6, they discovered that SF6 is a greenhouse gas and it's terrible for the environment if it leaks. That means what? That means we have very sophisticated SF6 leak detector, and a lot of the substation is called GIS, gas insulated switchgear, or gas insulated substation. So again, that's a very important tool because number one, you have to report all the leaks, and number two, if you're not careful and you have enough leak, and if the pressure drops significantly, the insulation may be at risk. The emergency generator, the example I gave, again, you have like either it physically exists. So usually, if you know anything about the generators, it takes a long time to set up, to test, a lot of money, a lot of people get involved. But if it's already connected, you send the signal and it runs, and you'll be able to see from the SCADA if it works or not. The station light and power, as we spoke about before, most utilities, they have at least two of them, are supplies from two different circuits. That's very important. Now, the breakers, so one thing that we didn't discuss a lot is the inspection cycle. Equipment have different inspection cycle. They have a visual inspection cycle, they have testing inspection cycle, and they usually have a longer duration cycle when they basically take the equipment into pieces and put it right back. It's almost like taking your car for like a full tune-up, that they check everything, they make the necessary changes. That is usually the last one. So breakers are, the latest in breaker technology, they're able to skip a lot of this inspection because number one, they're always monitoring the flow of power, and so they always measure, when there's a fault that happened and the breaker operate, you're able to know from the way it operated if it basically requires additional maintenance or not. So again, Just the fact by relying on this, all these tools usually are self-diagnosis, and most of them, at least on a pilot perspective, they are available. So again, that's a very important point. Transformer, I mean, the one before that, anytime you have a failure, there's a lot of steps. The failure happened, the control room operator looks at the SCADA, they make sure the breaker is open, they send an operator to the field. He or she needs to check the substation, make sure it's open, rack it breaker, rack it out, add all the safety tags, and then get the data for system protection. They don't access it remotely, so you have to download. There's so many steps for something that happens pretty much every day. So in my opinion, like if you have like an intelligent substation, you have to automate a lot of this stuff. Otherwise, it doesn't make any sense uh, because there's nothing really too intelligent about it. It's just a very mundane task. Uh, the transformer, again, the king. Transformer gets the most attention, the most investment. And I just want to bring to your attention something. Think of a transformer as the engine. And if you've ever been to a transformer, there's a lot of stuff on top. So think of all the stuff on top of part is the rest of the car. You could have the best engine in the world, but if the battery is dead or something is wrong with the radiator, the car is not going to go at all. And that's kind of the point here. The transformer has a lot of stuff. So as long as we monitor all of them, then we're going to be good. We also have load tap changer, which I'm going to talk about later in the voltage. That's very important as well to monitor. The infrared cameras, they do a good job because they can kind of see all the bushing and all the voltage. So you also have the disconnect switch. So a lot of times when you open, and right now the job is done, you're closing the switch, there's always an energy control center operator command to go and make sure it's locked closed. Now they take a visual look. In my opinion, if you have like an infrared camera, you could really tell if it closed properly or not. A lot of times you have events, like you get, the next day on the safety call, oh, feeder X, Y, and Z tripped and reclosed. And then a lot of times you want to know, okay, what happened? Was there any lightning activity? So that's what the utilities do. To be an intelligent, you either have your own weathering station or you basically keep track of the weather events. So a lot of time, all the stuff is being calculated and stored remotely. Pothead, POT stands for point of termination. Basically, anytime you transition, let's say from overhead to underground or underground to overhead or GIS to ISO, anytime this medium is changing, you have this device. Now, historically speaking, this device has not been the most, I would say, like the most reliable. They do fail a lot. So a lot of utilities have basically invested in making them more reliable. So I'm going to stop here for a second. Again, I know it's a lot to see if there's any questions before we move forward. All right. Again, the list continues. So here's a picture of the battery room. If you've never seen one, that's a lot. A lot of a lot of batteries, and of course, the larger the substation, and the larger the number of breaker, the larger the battery. Right now, recently, especially, we had like I said, you have the event of the substation shooting. So a lot of utilities are investing a lot of money in substation security. They put cameras, they sweep. I personally am a big fan of having the AI cameras because they do a lot more. They look, I've seen it before. They look at people, they look at like the license plate. Sometimes they do a quick matching of license plate compared to employees and contractors. And if there's something, a flag, like, the car is stolen or something. So there's a lot of stuff we could do. We lose a lot of power. We lose a lot of, sometimes the station goes down because we have an animal contact or like a snake that decided to rest on a transformer or a squirrel or something. So the good news here is that there's updates. There's animal guards, there's lasers, there's acoustics. So that we are doing stuff to accommodate stuff like that. The voltage, again, the CTs and PTs, we are installing the capacitor banks. I'm a big fan of a post. So notice the last couple of points I mentioned, you're not physically installing anything, but you're making use of the communication, if you will, and the intelligence. There's a question. That's a great question, Raja. And that's the point I mentioned earlier that I'm not a big fan of just relying on O&M. Number one, a lot of the software, remember, it's a hardware and a software. So they do require, number one, they do require calibration, they require maintenance. If you know anything about the firmware update, remember, Many of you guys will have Windows, then you install like the latest batch. It's almost like your iPhone. Every time I update my iPhone, it gets slower. So yes, there are issues. So it's not like it's gonna fail. So of course the equipment are more reliable, the actual transformer, but those are like additional alarms, really. I mean, think of it from that perspective. Like how often does your car, for example, sometime you hit like a speed bump and then all of a sudden you have a couple of check engine light comes in and then it resets. So I think overall they are reliable, but they have a very limited short time frame compared to others. They require a lot of babysitting, a lot of software updates, hardware updates. So that'd be the challenge. But this is a great question. Again, here I'm a big fan of having something called like a drone in a box. Imagine going back to Paul, he's the new operator. He doesn't know what's going on, but he knows there's a drone there. He clicks a button, the drone goes live, goes up, and provides a lot of intelligence. Again, as far as the weather stations, I personally could tell you we don't like any longer. We don't go like in the weather app on our iPhone. We have a lot of services that we use. Some of them are not very accurate, so now like utilities are installing their own weather stations. Excellent question again, Rogers. Usually there may be or there's not actually, we don't put more than one monitoring except the DGOA. So DGA is the dissolved gas oil analysis. Basically, it's always taking samples of the oil in the transformer. That's the only one I have seen so far that utilities may put two of them instead of one, but the rest we don't really have any kind of we don't put like another maybe the communication. A lot of times there's like communication line A and B. So that's kind of the design from the utility from day one. But as far as the monitoring, we don't like we're not gonna have like two infrared cameras instead of one field. But great question. Uh, Now the whole machine learning and AI is another important point as well. So just a question for the group. Let me know if you guys would rather take a break or would rather me keep going and then like finish like 10, 15 minutes early. Just put in the chat, please, like break or no break. I'm gonna keep going till you tell me. Flood happens a lot. So, we did after Superstorm Sandy, a lot of utilities invested a lot of money. Okay, thanks, Thomas. All right, so we'll take one more. So basically, sometime you have like this gate, like a submarine. If you've ever been to the Midtown Tunnel, there's this massive gate that was done after Sandy. Thank God we haven't used it, but the idea is if there's a lot of rain, it's gonna close. So there's a lot of stuff that we do like this that are very essential as well. All right, the communication, again, the question was asked, now another interesting thing is for an intelligent substation, remember, when you build a substation, you have to get the approval from the town and the boards. And recently, they were kind of anti any new station. So what they end up doing instead, they may request, okay, I need like a nice looking substation. There's always a fear that if a utility adds a substation in your neighborhood, your house value will drop. And I don't blame them because some substations are ugly, they're massive. Now you have a lot of trucks going in and out. So they may require like solar on the panels on the roof. They may require electric vehicle chargers. So they do a lot of stuff like that. Also, another interesting concept is called the digital twin. So we enable all the senses, all the communication. It comes back, and you could imagine the operator is like the Matrix, and he sees like live, like a model of all the substation as well. Again, just to highlighting the offshore wind, it's in the middle of nowhere. So this is the system would have the most automation. So again, unfortunately, we only have like one very small farm. So that's not going to have a lot of intelligence. But when you go really big, as New York and Jersey are expecting, we'll see. All right, so I only got one, but I guess you guys agreed with Tom. So again, I'll target basically finishing like in 45 minutes. Maybe I'll finish in 30 minutes to give you guys time for Q&A, and then we'll end up like around 45 minutes. So like I said before, I have some kind of quick formulas that is kind of a quick way of thinking. So the first one is the future is 3D. The first D is distribution. The second D is DRs. The third D is digitalization. So again, when you talk about, just to let you know, intelligent substation, like 98% of the time, the focus has always been transmission first. It's never going to be distribution first. And why is that the case? Because the distribution system, pretty much, if a station goes down, yeah, it's bad, of course, you lose customer, but that's not the end of the world. But if you lose a transmission station, it could impact multiple substations. That's kind of in a very high level. That's what transmission supplies a very large number of distribution system. So if the transmission goes down, then we're gonna have an issue. Also, all the solar, FERC 2022, there's a lot of stuff that we're adding in the grid, and pretty much most of the stuff are being connected to the distribution system. You're not going to have an electric vehicle connected basically to the uh, transmission system. That's another like very, very important point that I just wanted to highlight. You're going to always see them go into the distribution system. Now, of course, it goes without saying, if the distribution system, if the transmission system is stiff, this is the technical term we use, stiff. That means the voltage is very good, then you'll be able to accommodate more in distribution. So again, the stronger the T, the stronger the D, but not vice versa. The last D, so again, the second D is all the renewables, solar, wind, energy storage, electric vehicles, natural gas that is clean, supplying fuel cells. And the last D is digitalization. So technically, the one thing we're discussing today, that is digitalization. So back in the days, you used to have like an analog meter. It's very hard to read. Is that 80 amps or 110 amps? Now it's like 80.0568. So that's kind of what we came up with. So there's just a quick thing to remember. The other point is data. So data is basically that's a very important point. So number one is it's not enough to install the meter. You gotta do the transformation. So you're gonna start now taking all the analog point to digital point. And then what you really after is the fourth bullet, automation. But I could tell you, having been an operator myself, nobody likes the A word. You'll be surprised how many manual processes are followed at the control room for stuff that could be easily automated. For example, you could have a disconnect switch, like I showed you in the picture, and it's a motor operated. So you could just click a button, it opens or closes, but the operators don't trust it. They still want somebody to go in the field. So it's going to take a lot of effort to convince the operators. I am optimistic because the new generation, they're more onto communication and data, so they would probably trust their data. So again, data is everything. I just want to make sure this point is clear. But data is the present, the past, and the future. So that's a very important point. So having said that, sometimes you need to think a little bit differently because, for example, the whole era with COVID forever changed the data. So whatever happened before COVID, the data doesn't really look the same after COVID. But again, right now, a lot of utilities have finally installed AMI, which is the wireless electric meters that we had. That is kind of very important because now we have a lot of intelligence coming. So if you have, like, for example, a 1 million customer in your territory, now you have a 1 million customer providing data like 4 times an hour, multiple. So you have so much data point. So the idea here is how do you connect this data to the substation? This is the absolute basic. Again, we're going to be talking for 2 hours. So all of you guys, if you are basically through a computer and this computer is plugged in, you're going to be paying the price at the end of the month for those 2 hours because the meter is spinning, but you only pay for the real power, which is the horizontal line. However, from a perspective of the utility, we always think from an MVA perspective. And especially if you look at the equipment rating, it's always MVA, which is the megawatt and the megavar. Now, I mentioned distributed energy resources. So, of course, you have the regular stuff, the real power, reactive power, voltage, but in addition, you also have the ambient temperature, the backup temperature, the irradiance, the wind speed. So there's a lot of resources, a lot of additional tools not tools, but a lot of metering data you get. As far as wind, the most important one is wind speed. So the most important thing for solar is the fourth bullet, the solar irradiance. The most important thing for wind is the wind speed. Now, when we have SCADA, that's another important point. SCADA varies significantly by the user. Again, I was an operator and I was an engineer. Engineering, I wanted every possible data point. Operator, they want the absolute minimum for them to survive. So they want basically amps and voltage. That's probably it. But the engineers, they want voltage, current, power factor, you name it. So it's kind of amps versus everything and operators versus engineers. We always have to look at normal versus emergency, the percent load for the station. So again, this is just the point here, and I hope you guys are getting the connection. Intelligence is not just adding metering, it's adding intelligence based on the stuff you already have. You could have data from a cap bank from the feeder. So right now I'm making basically use of data. And again, the list continues. I'm not going to go through each one of them, but the point I wanted to highlight here is that there's a lot of data available, but unfortunately, not all data comes back. So, just to highlight a couple of them, maybe in the middle, the whole idea of condition-based maintenance. So, the utilities used to have like ongoing maintenance, like once a month, once a year, very specific, very timely inspection. But based on all the data and all the models, they're seeing that some of the time you don't really have to. I'll give you an example: oil change. A lot of the German cars, you put like say Mobile One, you have to change the oil, for example, every 9 to 10,000 miles. Others, depending on the type, you go there every 3,000 miles. And sometimes, depending how you drive and the car wear and tear, you may have to go sooner. So that's kind of the concept. It's not like thou shall go every month. It depends on you. I'll give you an example. When you next time you get an oil change, they're gonna tell you come back after a certain mileage or a certain time. And usually the time is very quick. Most of the time, I'm not even halfway of the oil and they want me to come back to change. So that's kind of the point of the slide is that there's a lot of analysis and a lot of the stuff is being done on this slide and the previous slide. That only happens for utilities that have data scientists. Otherwise, it's not your traditional utility people that could do something like that. So again, the list continues. I'll give you an example. So the overhead transformer, like right outside your house, utilities never put any SCADA there. There's so many of them, it's not really worth it. However, we have AMI data. So if I know that this transformer supplies 3 homes and I have the load for all the 3 homes, it doesn't take like a rocket scientist to basically add these 3 loads and know what the transformer is. So that's kind of part of the latest. And you could see here, we're putting a lot of sensors. Sometime uh, intelligence is knowing if an equipment drops. I'll give you an example and then I move on. If you've ever been to a substation, you're gonna see that transformers, they have a lot of fans. And depending on how hot it gets, those fans run more. Sometimes there's 3 sets of fans, and after a certain temperature, they would kick in. You'll be surprised how much the system will be derated or the capacity lost if those fans are not working. Um, One thing I'm working on kind of in my spare time is what is the age of the transformer? Not when it was built or delivered. What is the age? I'll give you an example. When you go do like a physical exam, 2 people, same year of age, one person is very healthy, the second one is not healthy at all. Again, they're both the same, but yet technically one is much younger than the other. That's kind of the concept here. Knowing all the previous data, the previous falls, did we ever exceeded any kind of temperature? I think some questions were about the temperature of the transformers, right? What's the load factor? How high does the transformer get? And then, for example, we have electric vehicle. We have a lot of stuff happening. PMU stands for phasor measurement unit. They are multiple data points per second. So some transmission systems, they have that. So now we're going from having no data to 15-minute data to like 30 or 40 data points per second. So that's kind of the point. So that was a lot. Let me see if there's any questions. Okay, now the next version of intelligence is knowing how your system behaves, knowing the supply feeder to the station and the individual feeder. So here's an example of a feeder. What does this feeder tell us? That kind of from like midnight to maybe kind of like 11 a.m., the load doesn't change that much. And then from 11 a.m. to like 5, it's going up, but it's minimal. But then after 6 p.m., then that when it picks up really. So that kind of tells you that this system peaks around like 8:30 p.m. And then it drops. There's a very sharp slope, if you will. That's kind of the stuff. So this is the beauty of data. If you only look at Excel without plotting, you're not gonna know that. From a reactive perspective, here's interesting part. Now, you guys should see something that should stand out right away. Anything that's interesting for you in this graph? So one thing should stand out. So this is a reactive power flow for one day for a circuit. So anybody knows what's so strange about this? Okay, so basically, just for the sake of time, what stands out is the negative side. If you look, this whole thing is negative. Let me see if somebody had a question. Okay, thanks, Thomas. Yeah, so pretty much you could see it's negative. So that means when you see negative reactive power, that means there's so much capacitance, there's so much capacitance that you exceed. You basically supply all the required reactive power for the circuit, and then you end up going back to the circuit. So again, if you don't plot the stuff, you're not gonna know that this circuit pretty much is oversaturated from the capacitor perspective. So again, that's the beauty of that. Okay, moving on a little bit faster. The voltage, again, we have ANSI standards and other standards that dictate how often the voltage drops or rises, especially if you have like a data center or pharmaceutical company or something nearby. So you kind of see here in this graph, there are a lot of spikes. So if you see a graph like this, that should raise a concern. Why is this system behaving like this? I could tell you because I know this system had a large solar site connected to it, and that day was a lot of cloud activity. So that's the point. So I saw the data, something flagged, I took a deeper look. Oh, it was a solar site. Utilities usually they have this what in front of you here for all the substation. That's like the typical substation load graph. It tells you a lot. It tells you, like at midnight, the previous day, the load was 85%. That's very high for midnight. So people are staying up late. Then there's a drop. Then it picks up again after 7. And then you have probably like over 12 hours when the load is above 90%. That's a lot. So that's kind of what the data tells you. And usually you should have this for every substation, every feeder. I could tell you just a warning that all the graphs before COVID looks different from after COVID, because we work from home, all this life changes and people moving, that became a big deal. Here, just to kind of show, now in blue is the solar graph or solar generation. In red, that's the circuit where the solar is connected to it. As you could see, basically when the sun is available and the sun is supplying power, the feeder is supplying less and less power. And then later on in the day, the sunlight or the solar radiance drops. So as the solar is dropping, the feeder is picking up load. The idea here is that the customer doesn't lose power. So no, that's a good question. So yeah, what happened is I mean that solar graph was way before EVs were a thing. But anytime you see an uptick at night, and this is kind of sustained, most of the time that's because of an EV load. And that's a great question. We're able to actually see that uh, all the time when you look at the AMI data, Thomas, because we see like this is the typical load, like the average home peak is like 3 kW, but the level 2 charger could be like 17. So all of a sudden the house load would be multiplied by 5. So, but that's a great point. So as far as the future, there was a period of time like 3, 4 years ago, if you guys remember, they were talking about the transmission system would be a stranded asset, the substations are no longer needed. And then all of a sudden everything changed with the load increase, the stuff that I mentioned before, AI and so forth. So I personally believe there will be more substations built. It doesn't mean that the overall number would be higher because, for example, you could eliminate an old station and then come up with one that is like 5 times the size. For some locations, that's something there'll be lesser substation because they're just bigger. There's definitely more substations that will be built to accommodate data centers, EV load, and renewables. That's a fact. Now, utilities have different systems. Some of them require, for example, the developer pays the utility builds the substation for them. Sometimes the substation is owned by the customer. Sometimes the substation is maintained by the customer. Sometimes it's owned and operated by the utility, but the customer pays for it. So there's a lot of different ways, especially when it comes to solar or renewables, that would dictate. So again, at the same time, remember, we have a lot of renewables, we have a lot of backfeed. So are we gonna have any issues in the transformer or not? As far as the future, again, I mean, why building stations? So I give some examples, but here's a good summary. Asset life cycle is basically the utilities looking at all the conditions that they have for the equipment and realizing that, guess what? We need to do something different. Our system is not going to last. The average age for a transformer was like 45 years ago, 45 years of age. Now it's 50, now it's 60. Some utilities have equipment that are above 90 years old. They were never designed for something like that. Resiliency, Mother Nature, right? So Mother Nature continues to attack. We lose equipment, we have damage, then we build a station which is more resilient. Load growth, just best example, look left and right. All these data centers are promising a very large number of substations. O&M, so let's go back to my Honda Civic. After a while, my car was costing me a lot because it's always getting fixed. It's always an issue. So after a while, you basically end up getting rid of it and then basically buying something else. Of course, it's going to be more expensive in the beginning, but along the line, it'll be cheaper. As far as future transmission, I mean, if there's one thing that you read about today, is the need for more transmission to accommodate again data centers and so forth. So we're getting lines from Canada to New York City, upstate to New York City. Texas is building a lot of lines. I heard this massive corridor between multiple states. So states are very busy adding more transmission lines. I don't believe you can have any stranded assets because every transmission line now provides a great value. So we're very, very far from every stranded assets. And again, remember, when you build this very large solar and storage and wind, you still need transmission to connect them. So here's a picture to kind of highlight a couple things. Resiliency, top left, you could see that there's so much snow that impacted the transmission. You could see the picture in the bottom right and top right, the flood. The picture on the left, you have debris. And this is the stuff we discussed in the substation fire grid damage webinar. So we have to act stuff like that. Again, when I think I was Paul or Thomas, if you're the new operator, remember right now you have the camera, you have a picture, but if you're flying blind and you get all the alarms, you have no idea what just happened. So if you ever purchase a car, I mean, one day I got a car through my dad's friend. It's the worst car I ever had. Looks great from outside, very neat. I've never had that many problems in my life. Everything was wrong with this car. Everything. And then a friend of mine he had a Carfax account. I gave him the VIN number, and we found out this car was stolen like more than once. So similar thing. What if we have a substation fax? When you know exactly the loading, how often you exceed the normal rating, emergency rating, what did we ever exceed the top oil or hot? So again, if I were to purchase a new utility or to merge with them, I would like to have this for every asset because those assets are very expensive, and when they fail, a lot of time it's catastrophic. So I hope you appreciate this. This is just kind of a concept I'm working on. As far as the infrared cameras, again, you could clearly see from the picture on the left, it shows you that one phase is running much hotter, and even on the right, one phase much hotter. So sometimes people misunderstand that the infrared camera is not there to tell you, oh, one is 45, one is 55. It's kind of a difference between the two. But it would flag something like this. So for example, maybe the job, they just had a scheduled job and they done it, but the phase on the right was not done properly. So there's some kind of arcing, that's why it's hot. Again, it's 24/7 every day. They provide great value. You may put an infrared camera to look at a certain component, but the fact the camera is there is basically it's looking all over. So they may pick up something that was not even the goal. Again, that going back to Paul and Thomas as the operators, it's one thing to get an alarm, but imagine getting a live feed. How amazing is that? Instead of just getting an alarm, you literally have a camera that's providing you the phases. You know what's going on. You can make a very educated guess organ analysis then. Again, it's enhanced visuals. Technically, I mean, they're easy, but they're not that easy because sometimes when you work with developer, depending on what you're really trying to focus on and monitor, sometimes the camera may require a transmission outage to be installed. And for some locations, like in PGM, you have to tell them like 6 months in advance. So transmission, it's not forgiving when it takes a very long time. Again, anything we could do to reduce the O&M savings, the mileage traveled by vehicles, any kind of possible failures would be great. Again, if somebody jumps in to steal copper, you can have the camera there anyway, which is the security camera, but some of them now are dual cameras. It acts as security and infrared as well. So that's kind of how it looks like. So again, this is an example, right? So on the left, not that crazy, right? So two of them are relatively hot. One of them is not that hot, but so again, depending on the load, depending on the balance, maybe two sides have more load than the others. That's kind of the value. The picture on the right, you could see two of them are very bright. The one in the middle is not as bright. So again, it's the beauty of the difference. So I mentioned COVID multiple times. Yes, it has been many years then COVID hit, but the impact that I'm saying is, customer changed. Some people left altogether, so the load dropped. Some people moved, so the load increased. Some people work from home all the time, so now the residential substation, the load increased, and so forth. You could have an essential employee and not essential, but every substation is essential, even if it's not as important. If you lose that unit substation, I gave an example before in the beginning, you may lose the mall. The mall has, the clothing, the food. So for the town, at least, that's a big issue. So if you remember during COVID, life went on as long as you had reliable power, fast internet. And initially, you were able to work any place in the globe. Some people went to like cheap areas, resorts, but now, I mean, the vacation is kind of over. So kind of wrapping up towards the end, you can start the Q&A. When the whole COVID happened and the whole point of essential workers, I think China was kind of displaying how way ahead of they are compared to others, that like basically COVID did not cause a problem because they already had a lot of robots, deployed at a lot of substations. I mean, that time, I think they at least posted this like 60 substations, which is a very, very high number. Of course, for China, it's not as high, but those stations may be very large, as you could see. So again, robotics is here to stay. So again, just to stress one more time, the 100% clean energy that used to be 2050 is now basically it's 2035 or sooner. So you have the future customers changing. The customer wants basically in their desire, they want 100% available power at zero cost. Now, that's not real anyway, but if it's up to them, they don't really pay for stuff like that. The future substation must be intelligent based on all the stuff I said. Will be a lot of substation, a lot of transmission, a lot of distribution, but you need to maintain the reliability for the grid, the resiliency for the grid. You need to be able to maintain and allow more renewables, and you need a cyber resilient team. So every single substation, especially those are like, distribution and above, not like a unit substation, would require a lot of work. So just want to stop here for 30 seconds on this. This is important. So as far as the future customers, again, it's customers want renewables, they want solar, they want storage, they want like a lot of this cool stuff. I mean, they want to be fully connected. They're not very happy at all, when they lose power, which is kind of understood. They want to participate in the net zero. They want to pretty much make some money. So, like, if there's a market, like the transactive energy market or the renewable market, they want to sell their solar, their generation. Here, the picture in front of you, you can see like the Tesla energy storage grabbed by the transmission stations. They want to enable the electric vehicles and the vehicle to grid, which we have another webinar on. And then, they want AMI, but they want to get the data from the utility. They want to understand, it's one thing to tell me, for example, if you wash your laundry at night, it's cheaper. But imagine now telling me exactly, your bill for this month is $100. It's $10 because of this TV, $20 for this. Like you get a lot more intelligent. And by the way, your AC has an issue, and if you replace it, you'll save X, Y, and Z, which is known as the smart home. At the same time, the regulators, they're really pushing for this 100%. I mean, even now, we have like a different government entity, they're still pushing for that. Some commissioners, they would rather, and they would really hope for and aim for the 100% available grid. Imagine if we never lose power, right? That's kind of the argument here. But the problem really is that it's not, I mean, you could build a system like that, but do you have any idea how expensive a system that never fails? Now, technically, failures will happen, but the idea here is you have a very large number of redundancy, even on the customer level. At the same time, they want unlimited amount of electric vehicles. So now we keep adding more load, more load, more load. Do we have enough to charge it or not? I mean, the transformers are getting more efficient, but still, we're very far from getting the maximum efficiency theoretically. And then, like I said before, they want microgrids. They want the ability to disconnect from the grid when there's emergency and supply your own power. So it's a lot of stuff in the slide. And as far as the future transmission, whether it's underground or overhead, I kind of showed you a picture for robotics, but the use of robotics and underground to help with the splicing, putting like the small cameras along the conduit to find out where the fault is before doing any work. Splicing is a work of art. Sometimes, if you have a transmission failure, it could take a couple of months to fix. Can't you get closer because you have the cameras, you got the sensors, you find the fault very quick, then you have like this machine that goes then connects two ends, so there's no mistakes. We're putting out cameras inside transformers to see what's happening. Some utilities are investing in superconductor cables, which is basically provide like infinite power. Infrared cameras getting more popular. The vegetation, which is basically uh, making sure that there are no nearby trees or any kind of issue. So again, this is if you work in the transmission business, you'll appreciate this. We basically took every issue there is, the sagging, okay, let's automate it. The underbuilt, okay, I don't want anything under. So, and then we address it. That's kind of the beauty of the job that I do, is the planning for the future. Now, you cannot have a future if the weather forecast is very poor. That's why utilities are putting their own weather stations. We're installing drones, we're doing better tree trimming, and so forth. So that's kind of the point, that kind of the focus here is, our preparation for the 100% systems. So again, and then the other thing we didn't really talk much about today is kind of using like an X-ray. So right now, X-rays are more common. Before you start digging the street to find the transmission fault, you take like an X-ray picture to make sure that the fault is there. During COVID, there was a rise of using the 3D glasses and the virtual reality tools, so as if you're physically with your team. So overall, climate change, I mean, it's here to stay. That we're still seeing damages every day. We're seeing season shifts. This year, the winter in New York was brutal. We did not have like a single warm day versus I think like the last year, the day before, we had many, many, many nice looking days. We're seeing like snowstorm for the first time ever in Texas. So, and the number of storms are on the rise. So this kind of focus that but one of the biggest threat. I mean, you could put all the intelligence you want. It's not resilient the next. And of course, to basically curve is developing something called the management. So here's ERMS, Distributed Energy Resources Management. It's a very long name. It's known as DERMS. Basically, what it does, okay, I'll ask the question, Roger, in a second. So what it does, software only mode. So, engineers and others not just operators could use it to see the and as far as cyber, that's science by itself. It's broken down by transmission versus distribution, broken how vulnerable the, the utility is. So again, the unit issue somebody pretty much could hack and disable like system protection. Again, remember, renewables are getting overall cheaper. So in the substation, it's it's a nice looking substation. It's a nice looking fence. It's LED lights. It's physical and cybersecurity. Substations, but many of the utilities who tried that, they basically were suing that because they had your basically the solution failed and the station pretty much burned to ashes. So the reason people like options is because it's a push for us to make more more Right, so apologies, I was just talking about technology and my computer disconnected for some reason. So let me go back. Uh, I'm just gonna share my screen and then we'll get going. Thank you. Yeah, sorry about that. I'm not sure what happened to the screen. Um, okay, let me just share my screen. Yeah, let me just share my screen for now so you don't waste time. Okay, so we were just mentioning just before we get disconnected that we have to pretty much look at beyond the technology, the weather and stuff like that. So overall, the price of the solar and renewables are dropping. That means more will be connected. Like I said, as far as offshore wind is an unknown. I mean, there's a lot of onshore wind in the country. Supply chain is a big deal. With all the delay to build the substation, that's very, very critical. The fuel cells, the DGs, the big data, all the stuff really will play a very important role as well. And then, like I said before, the transmission impact distribution, distribution impact transmission. You also have, issues with the voltage, the thermal. Again, are the existing regulation, the voltage regulation tools, are they sufficient? Or do we basically need, faster tools? So I'm working on a lot of electronics. So that's another thing, the role of electronics. Here's inverters, as I mentioned. So we're seeing a lot of inverters. So there's a lot of electronics being added to the grid. So what do we do from that perspective? Again, IT, as I mentioned, IT, I say they fear the S word. So the S word is security. So a lot of time, there's really, you have to work with the IT. That's the biggest issue. Like every vendor I've worked with, IT had to be part of it. IT had to approve it. So that just to get the cybersecurity blessing may take sometimes over a year. And I guess the kind of the great question, typically, if you know, software, they have a life of like 7 to 10 years. So a lot of the tools we're adding, number one, a lot of them are brand new. So they have never really been tested like in a very nasty environment. Storms, wind, there's a lot of stuff that happening, vibration, dirt. But from my guess, 7 years would be the average number. That's why I'm saying if your job is just to reduce O&M, may not be the case. And then very important here is data analyst. If you don't have someone to look at all this data, then all you have is a lot of stuff coming in with no intelligence behind it. Transformer is the most important equipment. There's no question asked. So we spend the most focus on the transformer. The most intelligence goes to the transformer. The bushing, the fans, having like I said before, there was a question about using multiple resources, more than one, DGOA and so forth. Right now, there's a big issue with the supply chain because it could take double or triple. You may have to wait 4 years for a transformer. So you don't want to be that one engineer who missed the alarm and then lost like a $10 million transformer and then have to wait like 4 years. Having fun explaining this to upper management that the transformer is going to arrive by the year 2029 for something as simple as missing an alarm. This slide is important. Again, the example I gave you, so the transformer is the engine, but you could see here there are external and internal stuff. So we have sensors for the tank, for the bushing, for the radiators, for the pumps. And that's why the transformer by itself is a whole, it's a whole world from an intelligence perspective. At the same time, the transformer outside your house, that's what I'm showing here. There's really no need for a lot of intelligence. Like I said again, if it's connected to two homes and I have the load from two homes, then it doesn't take much to invent. So that's the point here is that intelligence is not a generic thing. It costs money. So again, the power flow, I think there was a question about power flow. So now after the 2003 blackout, the utilities, we spend a lot of money basically to put the PMUs and the sensors from bus one to bus two. So now we have the intelligence, about the flow from different substations and so forth, which plays a very important role. I mean, and thank God since '03, we didn't have a major event, but having the PMUs at different substations, we kind of know how stable the system is. As far as ratings, again, normal rating, emergency rating, your system is only as good as the weakest component. That's for sure. So, uh, so there's a question about If you mind, Raja, can you I'm not sure if I understand the question when you say, can you like just rephrase the question? I mean, are you asking about the tap changer? If you don't mind, and I'll answer it right away. So again, here, you cannot have an intelligent system if you don't know your weakest component. You could have a brand new car, the car could go like 260 miles per hour, but there's one issue, one missing component or something, an issue. So until you fix the issue, that's the whole point. We cannot push our system beyond its limits unless we know of every component. There's now FERC Order 881 and the whole dynamic line rating, that's going to play a role as well. So again, how do you regulate the voltage? You have the transformer tap changer, you got voltage regulator, you got capacitor banks, you got shunt reactors. However, now you can see in the picture, we have StatCom, which is device on the left that moves like 30 times per second. You got small inverter, large inverter, energy storage, large one behind the meter. So here, the point I'm showing you is that the system has changed significantly. And remember, you could say, okay, look, be aware of it. And again, as far as the look point, yes, you have, and then let me turn off my camera so you could. However, energy storage still relatively new. It's still expensive. The price is definitely going unless the commission, like for example, Texas has a lot, New York has a lot. The commission really has to up. Yes, but energy storage does help a lot, which definitely for sure. Again, going back to the robotics before we end, to the pictures I showed you again, that was from China. You could kind of tell from the picture on the right. This station most likely is a 765 kV. It's a mess. So again, robots are being used at very, very large sites. So again, and the more you use it, the more experience. Again, I gotta give credit to China. I mean, a lot of us are using drones now, but they're taking it like, 10 steps ahead. They have this like flamethrower that if anything kind of hanging on a transmission tower, instead of getting like a very large bucket truck in the middle of nowhere, the drones are able to kind of basically burn off. So again, there's a lot of lessons for us here to learn from others. I was very surprised during COVID that some people in China they were able to continue the construction. So they were controlling and driving cranes from home. I know it's kind of dangerous to live in a house or a building that the crane driver was doing it from home, but here's the example of 5G was been fully utilized. You also have this example of the robots, the multiple, you would never know substations. Yeah, I'm sorry about that. So that's kind of like the last slide anyway. So as far as the pretty much the future, it's all about artificial intelligence. So AI is getting a lot of popularity now. I'm doing a lot of work with EPWI from that perspective. Cyber resiliency. There was a question about cyber. Cyber is playing a very, very important role. Having this live feed, drone in a box, or having basically the smart intelligence. Uh, it's very important for us to have the infrared cameras. I'm a big fan of the post-failure advanced protection, the bullet from the third one from the bottom. We need to automate this. We don't want to wait till we don't want to send operators anywhere. If you take with us the substation fire damage webinar, you'll see why it's very important, because a lot of times you cannot physically get to the station. There's a flood, there's a storm, there's earthquake, there's volcanoes. There's an issue with the ocean. So again, I hope that was helpful to give you kind of a flavor. If we were to have this discussion, I would say in the next maybe year or so, the only other difference would be a lot of AI related data center substations, and the major difference would be more power quality sensors to make sure you don't lose power at all. And at the same time, they're also going to have a lot of focus on reliability and backup resources. So I know we answered a lot of questions, so I'll stop talking here. See if there's like any last minute questions you guys have before we wrap up. So the floor is yours. Yeah, I mean, cybersecurity Thomas, a great question. It's very generically. So you have like a cybersecurity team. It's broken down by 100 kV and above, 100 kV and below. So the bulk electric system and then distribution. Like I said, we're talking about a lot of intelligence. So part of it is all the aggressive, kind of process that they have to go through for the vendors to be accepted. That's not an easy thing. I told you sometimes it could take over a year. So that's kind of really what's happening here is all the work that's being required for them to become approved as a vendor of choice. We do have audits, so they do have what's known as vulnerability studies and gap analysis. So over time, they look at all this information to see if there's any gaps. Anytime one of these vendors has been hacked or their subcontractor, they're basically taken offline. And then of course, as long as you are in NERC compliance, which means you have very aggressive cyber resiliency. So that's kind of all the stuff that is done to accommodate that. But that's a great question. Right, so I'll wait another minute. Is any other question or comments? I'm trying to be respectful of your time because I know you guys wanted to skip the break. And again, apologies for this connection. I'm not really sure what happened because that's like a brand new computer, so it shouldn't happen. All right, so again, it's been a pleasure. Feel free to reach out if you have any questions or comment after the webinar. You're gonna have the slides, and also we'd love to see you in a future webinar. So I'll pass it back and thank you very much. I know they just posted in the chat kind of this direction for the next steps. So let me know, please. Again, we'd love to work with you guys in the future. Have a great day. Thank you.